We now discuss the two-way factorial experiment. Factorial experiments are valuable designs when simultaneous conclusions about two or more factors are needed for certain experiments. A two-way factorial experiment is an experimental design in which two independent variables, that is, factors, are investigated simultaneously to determine the effect on a dependent variable, that is, response variable. In this design, all possible combinations of the levels of the two factors are tested. For example, in a two-way factorial experiment, we might be interested in examining the effect of two factors, A and B, on a response variable, Y. Factor A has two levels, A1 and A2, and factor B has three levels, B1, B2, and B3. The experiment will involve testing all possible combinations of the levels of the two factors, resulting in 6 treatment groups: A1B1, A1B2, A1B3, A2B1, A2B2, and A2B3. The two-way factorial experiment allows us to assess the individual and combined effect of the two factors on the response variable. This design is useful when there's a suspected interaction between the two factors, meaning that the effect of one factor on the response variable depends on the level of the other factor. As illustrated in this graph, a two-way ANOVA includes A levels of factor A and B levels of factor B. The experiment will involve collecting data on A times B treatment combinations. A treatment is a combination of level of factor A and a level of factor B. In other words, each treatment involved changing the levels of both factors A and B simultaneously, which allows researchers to analyze the main effects of each factor and their interactions. Factor effect and interaction are two important concepts in the analysis of two-way factorial experiment. In this type of experiment, we simultaneously study the effect of two factors, such as temperature and pressure, on a response variable such as yield. The factor effect refers to the change in the mean response as one of the factors changes. For example, if we vary the temperature in our experiment, we can measure the effect of temperature on the response variable. If we observe that the response variable increases as the temperature increases, we say there's a positive factor effect. On the other hand, if we observe that the response variable decreases as the temperature increases, we say there's a negative factor effect. Interaction, on the other hand, refers to the situation where the effect of one factor on the response variable is not the same at different levels of the other factor. For example, if we vary both the temperature and pressure in one experiment, we may observe that the effect of temperature on the response variable is different at different pressure levels. This means that the effect of temperature is dependent on the pressure level, and there's an interaction between temperature and pressure. In other words, an interaction occurs when the effect of one factor on the responsive variable is not constant across the different levels of the other factor. If there's no interaction, the effect of one factor on the responsive variable is the same at all levels of the other factor, as illustrated in the leftmost graph. The presence of an interaction can complicate the analysis of the experiment, as it means that the effect of one factor depends on the level of another factor, as shown in the middle and rightmost graphs. However, it also provides valuable information about the relationship between the factors and the responsive variable. In a two-way ANOVA with repeated observations, we consider two treatment variables and the possible interaction between the variables. In this example with two factors, route and drivers, influencing the response variable, travel time, there could be another effect that influences the travel time. This is called the interaction effect. That is, differences in travel time may depend on the combined effect of driver and route. To create an interaction plot, the routes are labeled along the horizontal axis and travel time along the vertical axis. Each line plots the mean travel time for each driver for all four routes, with a different color lines for each driver. Because the five lines are clearly not parallel, there's an interaction effect of driver and route on travel time. The travel times that depend on the combined effect of driver and route. To test for interaction, the sample data must be replicated for each combination of the two factors. For example, in a study with two factors being tested, each driver would drive each route 3 times. This results in 3 observed times for each combination of route and driver, with m equals 3. Replication enhances the experiment validity and reliability by ensuring that any observed effects are not due to chance variation. By analyzing the replicated data, researchers can determine if the effect of one factor on the responsive variable depends on the level of the other factor, indicating an interaction. This information can provide a deeper understanding of the relationships between the factors and the response variable, allowing for informed decisions based on the experiment result. The ANOVA procedure for two-factor Factorial experiment is similar to that of a completely randomized experiment and a randomized block experiment. The total variability is divided into 4 components. First, the variability due to the main effect of factor A, denoted by SSA. This component represents the variation in the response variable attributable to the different levels of factor A, while keeping factor B constant. Second, The variability due to the main effect of factor B, denoted by SSB. This component represents the variation in the response variable attributable to the different levels of factor B, while keeping factor A constant. Third, the variability due to the interaction between factors A and B, denoted by SSAB. This component represents the variations in the response variables that cannot be explained by the main effect of factor A and factor B alone, but is instead attributed to the interaction. Fourth, the variability due to the randomness of the sum of squared residual, SSE. Thus, we have SST equals SSA plus SSB plus SSAB plus SSE. The total degrees of freedom, N, T minus 1, are allocated as follows: A minus 1 degrees of freedom for factor A, B minus 1 degrees of freedom for factor B, A minus 1 times B minus 1 degrees of freedom for interaction, and A times B times R minus 1 degrees of freedom for error. Here, M represents the number of replications for each interaction combination. A two-factor factorial experiment, ANOVA table, is a summary of results from a two-factor factorial experiment. The table includes the source of variation, sum of squares, and degrees of freedom. The mean sum of squares, MS, is calculated by dividing the sum of squares by its corresponding degrees of freedom. The F ratio is then computed by dividing the MS for each source of variation by the MS for the error. The p-value is obtained from the F distribution with the appropriate degrees of freedom. Due to the interaction effect, there are three F statistics. The ANOVA table is utilized to test the null hypothesis that there are no significant main effect or interactions between the two factors. Specifically, factor effect A, factor effect B, and interaction effect A and B. If the p-value is less than the chosen significance level, typically 0.05, the null hypothesis is rejected, and it can be concluded that there is a significant main effect of interaction. Returning to the case examining the interaction between route and driver, we observe that the F statistic is greater than the F critical value based on a 0.05 significance level. Consequently, we can reject the null hypothesis that there is no interaction effect between route and driver. The p-value of 0.0456, which is smaller than 0.05, further supports the significance of the interaction between route and driver.